So let's continue the discussion. At this point, we're building the conceptual base of quantum mechanics. Now, I discussed that there are different meanings of what a state of a particle is in classical realm versus quantum. In classical realm, you specify position as a function of time, and you have Newton's equations, for example, that tell us how that position evolves. In the quantum realm, you have this thing called wave function or probability amplitude that can give us statistical information about outcome of experiments. And nevertheless, you might say, well, look, come on, tell me, where is the particle? You might say, well, okay, fine, maybe the wave function is the right way to do it, but can you tell me where the particle is? And I will say no. The location of particle, it's not a well-defined question in quantum mechanics. So I cannot, and not just I, one cannot say before making a measurement where the particle is. And when you do make a measurement, the particle takes a stance. It acquires a well-defined position. And the wave function gives the probability distribution of where that particle will take a stance. So where is the particle? It's a meaningless question until you make the measurement. When you do make the measurement of position, the particle materializes, or it takes a stance. It can appear at different locations randomly, but the probability distribution where it will appear is given by the amplitude, by the square of the amplitude of the wave function. We can make other measurements. We can measure momentum. Okay? And then there is a probability distribution for that. It's not given by the wave function, it's given by something else. We can measure its charge, and so on. Well, with charge, there's not going to be a probability distribution, but we can make other types of measurements. We can make kinetic energy measurement. We can measure potential energy. We can measure all these standard things that are part of classical description. And then there will be probability distributions. In some cases, that probability distribution will just be a very sharp peak, so you always get the same outcome of the experiment. In some cases, there is going to be a wide distribution. And we will get there in due time. Okay, but I wanted to address the question of where is the particle? That's point number one. Point number two. Double slit experiments with electrons. So so point number one. Where is the particle? Not defined until a position measurement is performed. When a position measurement is performed, a particle takes on a particular position x with a probability given by psi of x quantity squared. Okay, so that's comment number one. Comment number two. So I guess I should say comment one. Comment number two. double slit experiments with electrons have been performed. But that is not how people learned about wave nature of electrons in the first place. The first experiment that was a smoking gun that showed that things that we think of as particles behave as waves was something called Davisson-Germer experiment. So you might want to add that to your list of big experiments of modern physics. Davisson-Germer experiment showed, first showed the first demonstrated the wave nature. I believe they did it with electrons. Now what they did, they didn't send electrons through double slits. Your textbook has a really nice discussion. I'm not really going to go into details of Davisson-Germer experiment. So this was 1927. Quantum mechanics was still being developed. And what they did is they performed diffraction of electrons off of a crystal lattice. Now, diffraction is a wave phenomenon. So if electrons were particles, you wouldn't, the outcome of what happens when you send electrons into a crystal lattice would be different than the outcome that you get when electrons behave as waves, because if electrons behave as waves, they will diffract. Remember what diffraction is. You will need a lot of that. Diffraction is basically spreading of waves when they pass through obstacles, openings, orifices, things like that. And so the outcome of the experiment showed that based on the locations of where the electrons were found, that could only be explained if electrons behaved as waves and diffracted off of a crystal lattice as waves. Now, nowadays that's called Bragg diffraction. Maybe you've heard of Bragg diffraction. The idea of diffracting waves such as X-rays off of crystal lattices was, I think at that point, was already established. And this demonstrated that electrons could also diffract as if they were waves, right? So what they did is they diffracted off of crystal lattice. Okay, and I'm not gonna say more, but actual double slit experiments with electrons have also been performed many times, some of them actually quite recently. And people continuously ask more and more sort of refined questions about measurements. And people always go to double slit experiment as a canonical experiment in quantum mechanics. Somewhere I heard someone say that, well, understanding a double slit experiment is sort of like equivalent to understanding quantum mechanics. Okay, so those are the two comments that I wanted to say. So your homework, the last problem on the homework, it may appear to be long, but it's basically a hands-on, quintessential learn by doing, a lab-like activity. Okay, it's not this class doesn't have a lab technically, so it's an assignment. It's an assignment in visualizing and understanding waves. We will need that. And rather than ask you to read the advanced section 2.7 of your textbook, I wanted you to just play with it, just learn by doing. At this stage, I think, based on where you are right now mathematically, and based on what we need, that might be more productive than you read about integrals in section 2.7. When you learn Fourier analysis in other classes, and you will have to learn it properly. But at this point, I think you will gain the necessary intuition by working that simulation.